So just to do a quick recap, one of the last things that we had talked about in section, 1.2, or as your textbook has it labeled as 5.2, we talked about the length of an arc or the arc length of a circle. And then building up on that, we had talked about how to find the area of a sector. And that's kind of where we had stopped at the end, was talking about how to find the area of a sector. So continuing with that same discussion, we're going to talk about linear and angular velocity. So obviously, when we're talking about a linear velocity, you can think about if a car is driving down the road, um, we would talk about its speed in terms of miles per hour, or maybe even depending on, what object we are talking about, we could talk about it in terms of meters per second. So these, measurements when we talk about miles per hour or meters per second, we're basically saying these are measures of a speed moving along a straight line, right? So therefore we call it linear velocity. But when we are talking about a point rotating on a circle, right, we would describe it as angular velocity or the rotational speed. Um, and these can be measured in radians per second, rotations per minute, RPMs, right? Or we can also talk about these in terms of degrees per hour. And, again, obviously it would depend on what kind of example we are looking at. So when we are defining, right. Looks like Bodhi just came in. So when we are defining the angular and the linear velocity, we are saying as the point moves along a circle with radius r. So if your circle has a radius r, its angular velocity, and we use omega as the variable for angular velocity. So omega can be found as the angular rotation theta based on the unit of time, right? So theta per unit of time, which will be t. And, of course, time can be, again, in hours, minutes, seconds, depending on what example you're looking at. So we're basically saying the angular rotation is based on the unit time. So that would be theta divided by t, right? So that's going to be your angular velocity. Now, linear velocity, we use the letter v, so the variable v for that. So the linear velocity of a point can be found by, of course, the distance traveled. And since we are obviously talking in terms of a circle, right? Your distance traveled in this case would be the arc length, so s, and again, based on the unit of time, so s divided by t. So you can see the two formulas here for angular and linear velocity. So let's take a look at an example here. You can see we're talking about a water wheel completes one rotation every 5 seconds. So they're asking us to find the angular velocity in radians per second. And if we actually click on this image, you can kind of get the whole image of, the water wheel we are talking about. So you can see, obviously the water makes the wheel turn. And then, of course, based on that, you will have your gears and stuff moving, right? So we're talking about a water wheel that has a one rotation every 5 seconds. So since we are talking about finding the angular velocity, obviously we're looking at this formula here. So if we are talking about one rotation, obviously, again, keep in mind working with radians, that one rotation is going to be a full circle, right? So 2 pi will be the angle measurement. So your theta then, of course, will come out to be 2 pi in radians. They are telling us that rotation takes 5 seconds, so that's going to be our time. So obviously, you can see that's going to be pretty straightforward. You take the angle measurement of 2 pi divided by 5 seconds, and we're basically saying the angular velocity as the wheel moves is going to be 1.257 radians per second, right? So this is just the speed at which the wheel is rotating. Now, we do want to talk about the connection between angular and linear velocity or the relationship between the two. So if you look at this little paragraph over here, we're basically saying, okay, we know the definition of the arc length, or the equation for the arc length is where we multiply theta with the radius of the circle, right? So if we can build up on that, we can get a relationship between the angular and linear velocity. Now, your textbook goes in a little bit of a, what I think as a roundabout way, but we can start with the initial formula for the linear velocity, which is of course given to us right over here. We know we define S as r times theta, right? So we've got our S as r times theta. But then if you look at the definition for the angular velocity, or the equation of the angular velocity, you will see we define angular velocity as theta over t. So instead of using theta over t, we can obviously replace that with omega, and you get the relationship that they are kind of talking about here. So like I said, they kind of go with, let's rewrite the formula with theta on one side and omega times t on the other, and then use that to substitute. So obviously it works, but I don't know, I kind of feel like this guy goes a little bit more straightforward. But it doesn't matter. You still get to the same conclusion where we get v, which is the linear velocity, is basically radius times the angular velocity, and you get to the same result. So this will definitely be something you want to keep handy, right, when you're working through these examples. So let's take a look at our next example here. We've got, let me clear this out. So we've got a bicycle that has a bicycle has wheels 28 inches in diameter. So 28 inches in diameter. We've got a tachometer, which determines the wheels are rotating at 180 RPMs, revolutions per minute. And they're asking us to find the speed the bicycle is traveling down the road. Now, of course, if they're talking about finding the speed that the bicycle is traveling, then of course we are asking to find the linear velocity, right? The v value of this. The angular velocity is given to us because they are giving you the revolutions or rotations per minute. So we do have the angular velocity. We just have to obviously convert it into a measure that we can use. So in this case, what you are going to do is you are going to start by converting RPMs into radians per minute. And remember, the simple conversion here is we know each revolution or each rotation is going to be 2 pi, right? So that's the conversion we need to do first. So you take your 180 rotations per minute and multiply it with 2 pi radians per rotation. And they're actually using, oh my God, I can't believe that word just flew out of my mind. Yeah, it'll come back to me. But we are using the units over here to kind of keep track of, the conversion that's happening from rotations per minute to radians per minute. So that's the reason why we are using this conversion where we know one rotation is equal to 2 pi radians. So that way your rotation as a unit can cancel out and you are left with radians per minute. And of course, 180 times 2 pi will give us 360 pi, and then, like we said, radians per minute. So now you have your omega. Of course, they're telling us the wheel is 28 inches in diameter, so we know half of that is going to be the radius. So your radius is going to be 14 inches. And then, of course, we are using this relationship formula here between linear and angular velocity. So you get 14 inches multiplied with 360 pi of radians per minute. And in this case, basically you will see we went from inches, radians per minute to just having inches per minute, right? So what you need to remember here is, remember, radians is technically a unitless measurement. There is no unit. technically for radians. It's just for our knowledge that we know instead of degrees, we're working with radians, right? So basically what happens is the radians just gets dropped, and you just go to inches per minute in that case. Okay, Ryder, I just saw your comment here. So didn't we say on Tuesday that 1 radian is 180 degrees, so that rotation is 2 radians? If that's true, then why are we using 2 pi radians? No, remember 360 degrees is 2 pi, right? So 180 degrees is half of that, right? So 180 degrees would be just pi. I think what you are thinking about is when we were doing the conversions between degrees and radians, right? Where we use the conversion of 180 divided by pi or pi divided by 180. So remember, a whole rotation around a circle is still going to be 2 pi, and half of that is 180 degrees, or half of that would be pi. So 1 radian is actually 360 degrees, or 1 radian is 2 pi. Ryder, does that make sense? I do see you nodding. Yeah? Okay. Did anybody else have a question on that? So we're okay on 2 pi being 360 degrees? Okay, alrighty. So obviously now you can see we have this conversion done, and technically you do have the speed of the bicycle moving down the road, which is 5,040 pi inches per minute. But obviously when we talk about speed, and obviously speed of a bicycle, we really wouldn't be talking in terms of inches per minute. So you can see that it makes more sense to convert this into miles per hour. So obviously, couple different multiplications will need to be done here. So obviously, we need to convert inches to miles, and you can see they went from inches to feet, feet to mile, and so we can get the conversion into miles. And then since our time was in minutes, we need to convert it from minutes to an hour. So you will see the conversion is going from 60 minutes to 1 hour. And that word that I had completely forgotten what I wanted to use was dimensional analysis. So this little calculation that we did, down here, but also the calculation we did over here, this is called dimensional analysis, where how you set up your fractions depends on which unit you want to keep and which unit you want to get rid of. The same thing we had done when we were converting degrees to radians or radians to degrees. So since we knew that we wanted to get rid of the rotations, we put rotations once on the top and once on the bottom, so they cancel each other out. That's the same thing that's happening here when we convert this from inches per minute to miles per hour. So you will see, since you have 5,040 pi inches per minute, inches is on the top. So when you set up your conversion from inches to feet, we put inches on the bottom, right? So they will cancel each other out. Then when you go from feet to mile, same thing, right? Feet is on the top here. So in the third conversion, we put feet on the bottom so that again, your feet will cancel out. So you will see inches canceled out, feet canceled out, mile stays back, right? So you will end up with miles in your final conversion. Same thing with minutes. Since minute was on the bottom here, when you set up this conversion, you put minutes on the top. So again, they will cancel each other out, and you will be left with hours on the bottom. So that's how you end up with your miles per hour. So this is what we call as dimensional analysis, when you have to remember how you set up your fractions so that when you multiply, the units you want to stay in the final answer, you will know how to set those up. And then you can see the bicycle is basically moving along the road at 14.99 miles per hour. So, approximately 15 miles per hour. So you can get that conversion. And what will happen here is you will basically end up taking 540 pi, multiplying that with 60 on the numerator. And then on the bottom, you will be dividing by 12 times 50 to 80. And that's what will give you the 14.99. calculation. So, and that's one thing about your textbook. I kind of wish they did not put this number in the center. I wish it would have been placed on the top so you would know that this is going to be part of the numerator calculation. But anytime in doubt, just put it over 1, and that way you know it's going to be on the numerator of your fraction. So do you guys see how we came up with the speed of the bicycle moving down the road? Like where the conversions happened and how we had to use the rotation of 2 pi to initially start our calculation? Okay. So this next example over here, they kind of give us a brief uh, outlook here, but let's kind of break it down a little bit. So for the 527 example, you will see it's telling us a satellite is rotating. Oops, sorry. A satellite is rotating around the Earth at 27,934 kilometers per hour at an altitude of 242 kilometers above the Earth. If the radius of the Earth is 6,378 kilometers, they're asking us to find the angular velocity of the satellite. So there's a couple different things that's happening over here. They're telling you that the satellite is rotating around the Earth at 27,934 kilometers per minute, right? So 27,934 kilometers per minute. They are also telling you, and this is going to be such a bad uh, drawing over here, but please stay with me. So this is going to be our Earth. They're telling us the satellite is about 242 kilometers above the Earth. So basically, if you're talking about, and that's the center of the Earth. Now, guys, we are assuming that the Earth is circular, right? Instead of its elliptical step. Yeah, very good, Nathaniel. That's exactly what you need to do. So we first need to find out the total distance that's going to be from us as the center of the Earth to the satellite. So yeah, you will be taking the radius of the Earth and adding that with the distance where the satellite is. So yeah, your radius is going to be 6,378, which is for the Earth, plus the altitude of the satellite. And of course, this will come out to be in kilometers, right? So you are going to take that total distance between the Earth and the satellite. So very nice. And then I will trust your math on that. So we have the distance. Now, obviously, when they're giving us the um, rotation of the satellite, remember they're giving us the linear velocity over here, right? Because they're just telling us around the Earth what distance it travels, right? And of course, kilometers per minute also kind of tell us that we are looking at a velocity, sorry, velocity over here as opposed to angular. And obviously, they're obviously in the question saying find the angular velocity, right? So remember, this is where you use that relationship again between angular and linear velocity to find what the omega will be. So this is the formula that's given to us. And let me see if I can do a scroll back to where we saw that. So right here, you can see V equals R times omega. So obviously that's the formula you are using here. And so what do you think that angular velocity will come out to be?
I got 4.220 radians per minute.
Alrighty. 4 point, say that again one more time if you don't mind.
4.220. I rounded up after
Oh,
the
you
correct.
rounded. Okay, that's why. Okay. All right, so let's take a look at that. So obviously, guys, you can do this before or after, whatever is more comfortable for you, but I would probably go ahead and divide both sides by the radius so that you can get omega by itself. So you can get omega equals velocity, sorry, linear velocity divided by the radius. And like I said, you can plug in the numbers and then do the division. It does not matter, but you're basically taking 27,934 and dividing it by that total distance, right? Which was the 6,620 and approximately you said 4.220. Um, and I can just show you that quickly on our Desmos here. So 27,934 divided by 6620. And yeah, you can see if you don't have the rounded answer, it's still pretty close, right? Because you've got the 4.2196. And as you guys are going through your examples, for problems like these, I would hope that they tell you what kind of rounding they want. So do they want 2 decimal places, 3 decimal places? Based on that, you should be able to come up with your rounding. And you can see in the example in the textbook, they left it at 4 decimal places, so 4.2196. And you should notice that the final result is in radians per hour, because remember, angular velocity is a combination of theta over time, right? So it's theta divided by time. So your theta is in radians. Time, of course, in this instance was based on hours. Um, Actually, it should be minutes because you had 27,934 kilometers per minute. And we did not do any conversion to change this from minutes to hours. So I would say that's a typo there. That should be in minutes, not hours. I will see if I can send a note. Sometimes with these OER, they have places where you can let the authors know there's a typo and they will usually fix it. But anyway, did anybody have questions on this? All right, guys. So that basically is the end of our section on angles, working with angles. And again, like I showed you last time, if you want to get some extra practice, you do have the questions at the end of the section, and the odd number solutions are given to you. So you should be able to verify, as you go through the math. So let's move on to section 5.3. And this is where you can see we are officially introducing you to some of the trig functions, beginning with sine and cosine. So let's talk a little bit about circles on a rectangular coordinate plane. That Nathaniel, actually, that does make sense. Yes, so it probably needs to be the other way around, where the typo is probably in the original question rather than in the answer. So yeah, thank you for pointing that out. I appreciate that. Alrighty, guys. So we are talking about, okay, so we have a point on a circle, and we're saying, okay, while it is convenient to describe the location of a point on the circle using an angle, or talking about a distance along the circle, basically we're saying relating this to the x and y coordinates and the position of the point on the circle based on those coordinates, and also using the equation of the circle that we saw in the first section. um, we basically build up on taking that putting it together and coming up with our application for trigonometry here. So they're saying, okay, what if there was a situation where you have a distress signal being sent out by a sailboat during a storm, and the transmission is unclear. The rescue boat is sitting at the marina, but they cannot determine the location of the sailboat. So using the high-powered radar, they know the distress signal is coming from a distance of 20 miles at an angle of 225 degrees from the marina, but they don't know what direction, right? Is it south, north or south, east or west? So they don't actually have the location specifically of where the sailboat is. So to build up on that, we're basically saying, okay, so we take our X and Y coordinate plane, right? So this would be your X axis. This is our Y axis. We start by drawing a circle centered at 0, 0. So of course, these points would be at your origin. You have your radius R, and you mark the point um, by using the angle theta, right? So you can see we have our point over here, we have our angle theta, and we have our radius r. So your point, of course, we know when we are working with the rectangular coordinate system, we put the coordinates in the ordered pair of x and y. So, alphabetical order, right? X goes first, y goes second. So now we're saying, okay, what if we take a vertical line and we drop it from where the point X and Y is to the X axis. So basically, you're drawing a perpendicular line from the point XY to where your X axis is going to be. And of course, you can see doing that will help us come up with a right triangle over here. And we know this is a right triangle because the angle the perpendicular line will make is, of course, going to be a 90-degree angle here, right? So we know this is a right triangle. So now we are saying it does not matter which quadrant your angle theta is going to be in. If you draw the triangle by dropping that perpendicular line towards your x-axis, all you really need to keep in mind is based on the quadrant, your x and y could be a positive or a negative value, right? So we do need to keep that in mind, but the angle itself is not going to change no matter what quadrant you are in. So it's just going to be those x and y values. Additionally, they are saying if the theta angle puts you on the axis itself, so if your angle is, obviously 0 degree, 90 degree, 180 the other value for, if you already have the x, the y will be 0. If you already have the y, the x will be 0, right? Because those will be the points that will fall right on the axis itself. So, think about this point here, this point here, this one here, and this one here. So when it's on the x-axis, we know the y value is 0, right? So you would have a negative x value here, y will be 0. If it's a point on the y-axis, then we know the x is going to be 0, y will be positive here, x is 0, y will be negative here, right? So they're basically saying, kind of keep that in mind if the angle leads you to one of these points, which is going to be on the x or the y axes. And obviously, again, based on where you are, you want to make sure your x and y has the positive or negative sign. So basically, you have your setup, you have your little right triangle showing up on your x and y coordinate plane. So now how do we go forward from there? So once you have your little triangles obtained, basically remember it does not matter what the radius of your circle is going to be. And remember, we talked about this when we first introduced radians. We said that the ratio stays the same between the sides of your basically the distance between the angle and the radius of your circle. So that same concept will apply here. You will have similar triangles, just, with different measurements because obviously the radius will be different, but those proportions will stay the same, which means If you look at the comparison between the radius and let's say side x1, and if you look at the comparison between radius 2 and side x2, those proportions, those ratios will stay the same. Yes, R1 and R2 will have a different value, X1 and X2 will have a different value, but proportionally, they will be the same. And of course, that's the same thing with Y1 R1 and Y2 R2. This concept of similar triangles and keeping those proportions same is what actually leads us into the discussion of sine and cosine. So if you look over here, we're basically saying if you have a point X and Y on your circle that has a radius R and it is at an angle theta, your sine function is going to be defined as the ratio between the y and the r values. If you think in terms of a triangle, remember the r represents your hypotenuse, and of course the y will be the longer of the, well, actually not necessarily because y could be smaller than x, depending on how the triangle is based, where the x and y value is. So I will take that back. It really doesn't matter if x is longer or y is longer, but your sine function will be defined as the y, the distance of the y value based on the radius of the circle, so y over r. And the cosine function will, of course, be defined as the x over r. So you can think of sine function with the y value. So, think of SIR, but with a y. And cosine will be with the x value. So I don't know if there's really a word that exists in the English language, but you can think of, I think of boxer, but with a C, so coxer, to help you kind of remember the relationship between X and Y values over here. So again, remember, it does not matter what the radius of the circle is. These proportions will always stay the same, which means that we can always use sine function as y divided by r and cosine function as x divided by r. And of course, you have this scenario where we are dropping that perpendicular line from the point xy to your x-axis to create that right triangle, okay? Um, yeah, Zadok, I will get to that in a minute. I'm trying not to jump the gun because I have a bad habit of doing that, but you are completely right. We will be using those definitions to describe sine and cosine functions. All right, let's clear this out. So again, as you kind of start, working with these sine and cosine functions, remember these functions can work both with circles and right triangles. We will obviously build up and get a little bit more technical as we move forward, but let's kind of go with what we have right now. So they're telling us, all right, you have a point 3, 4 on the circle. Your circle has a radius of 5 at some angle theta, because obviously you will see right now the angle theta is not going to matter. And they're just asking us to find what sine and cosine functions are going to be based on this information. So as you can see, the 3, of course, gives you the x value. The 4 gives you the y value. So you can just use radius, of course, is the r value, right? So you can do cosine as x over r. So that will be 3 over 5. There should be space or a comma or something in there. And then the sine function is y over r. So of course that comes out to be 4 over 5. So very, very straightforward, nothing complicated in this, right? Okay, so before I continue, any questions at this point in just a general definition for sine and cosine? Okay, let's build up a little bit on that now. So you've got so they're saying there are a few cosine and sine values which can be determined fairly easily based on the corresponding point of where it falls on the X and Y axis. So this is what I was talking about. So what if your point is going to be on one of the axes, right? So you can see this is on the positive Y axis over here. And this is kind of what they were talking about. Let me go back to that little paragraph here. Where did you go? Okay, right here where it says, additionally, if an angle theta puts us on an axis, so X or Y axis, we simply measure the radius as the X or the Y value with the other one being zero, right? So that's the same thing that's happening here. Since we know that this point, our angle is 90 degrees. So we know because it's 90 degrees, the point XY is going to fall right here on the positive Y axis, which means our X value will be zero and our Y value will be whatever is the radius of this circle, right? So they're not giving us a number, but we know that the Y value is going to be whatever the radius of the circle is. And then, of course, our X value is going to be zero. So when you are doing your cosine and sine function calculations, you can see that when we do cosine of the 90-degree angle, it's going to be X over R. Since my X value is zero, it really doesn't matter what the R value is, because remember, zero divided by any number is going to be zero. So it really doesn't matter what the R was. You're always going to come up with the answer zero here. For the sine of 90 degrees, you will of course do the y over r, but in this case, since the y value is the same thing as the radius, you're basically doing r divided by r, right? So the same number divided into itself, which would obviously end up giving you a sine 90 degrees with a value of 1, right? So cosine of 90 degrees is going to be 0. Sine of 90 degrees is going to be 1. So honestly, this will come out to be 0 and 1. Uh, it doesn't matter what the radius will be because, again, remember the proportionality stays the same, the ratio stays the same. So that's basically what's happening over here. Uh, does that make sense of why having the R value was not important in this example? Anybody have a question on that? Okay, all right, very good. Okay, so let's continue with that. So think about this one here. Now here they're telling us find the cosine and sine for an angle of pi. So let's do a quick rough sketch over here. Now remember the entire rotation. So if we start at, the positive x-axis and you make a full rotation and you come back, remember that in radians is 2 pi. So half of that is going to be pi, which means pi is the same as 180 degrees. So your angle pi is going to be right over here, which means you are looking at this point here, which remember I had told you, since this is on the negative x-axis, we know this is going to be a negative value, right? For the x and y, any point that you have on the x-axis, remember your y is going to be 0. So you need to remember that. And then, of course, whatever is the radius of the circle, right? It's going to be negative r for the x value. Pretty much the same thing you did in the example above, but here you were on the positive y-axis, so your r was positive. Excuse me. For this one, since you are on the negative x-axis, your x will be a negative value, right? So using those same definitions, your cosine of pi will be x over r. So as you can see, x will be defined as negative r. So when you do negative r divided by r, you get negative 1. And then for the sine function, so for sine of pi, we would be doing y over r. So of course, your y value is 0. So 0 divided by r will give you 0, right? So you can see basically you would end up with negative 1 for the cosine value and 0 for the sine value. So pretty much the same thing as the previous example, but you just changed the angle and brought it down to the x-axis. Okay, just waiting to see if anybody had a question on this. Okay. All right, guys, so let's see how we can expand based on that. So now we're saying, okay, you are on a circle with the radius r at an angle theta. So we can find the coordinates of the point x and y by basically rewriting the formulas that we just saw. So points on a circle that are at an angle at that angle using, so basically what you are doing, let me go back up here for a quick second. What you're basically doing is you're isolating the x and the y variables by moving the r to the other side of your equation. So think about this. If you multiply both sides of your equation by r, this is what you would end up with. So you would have x equals r times cosine of theta and y equals r times sine of theta. And basically, when we are saying if you are looking at a unit circle, again, to refresh your memory, when we're talking unit circle, remember your radius is 1. So obviously, these numbers would just become 1. So 1 times cosine theta, 1 times sine of theta, and your x and y values would be just cosine and sine. And this is, of course, for a unit circle. So yeah, like I said, you're basically just rewriting these formulas where you had cosine of theta as x over r. Just multiply both sides by r and you get this equation, and obviously the same thing for the sine function. Now, how do we tie this with the circle equation? So remember again, if you are a unit circle with a radius of 1, right? Actually, it doesn't have to be a radius of 1 as long as you are at the origin. I guess it wouldn't matter what your radius is. So as long as you are centered at the origin, remember your equation is x squared plus y squared equals r squared for a circle. So we are saying if you substitute the x squared and the y squared values with this definition that we just came up with up here, you can actually end up with, if you clean this up, so you can see we are replacing x with r times cosine of theta, and then we are replacing y with r times sine of theta. And then if you distribute that square value, you would end up with r squared and cosine theta squared. Same thing, obviously, here, r squared with sine of theta squared. Basically, factor out your r square from the left-hand side. So you can see we have an r square here. We have an r square here. You can factor that out. You would be left with cosine of theta squared plus sine of theta squared. Sorry. We're just factoring it from the left-hand side. So you're just basically bringing these guys outside, divide both sides of your equation by r squared. And you can see r squared goes into itself once, and that's where this 1 comes from. So you are literally taking the equation of a circle centered at the origin, and you can actually define it by using your sine and cosine functions, and you end up with cosine squared plus sine squared equals 1. And you will notice that we did shift the position of where you put the square. So instead of writing the square all the way on the outside of cosine of theta, you can actually write it in this format where I'm going to read it like it's written. So it's cosine squared theta, sine squared theta, but it basically means you are squaring the whole value, right? You're not just doing the square on the sine. It's just a short form of writing instead of having to write it out. this way, but that's exactly what we mean. So yeah, like they said here, that's just a shorthand notation of writing cosine squared, sine squared. And like they mentioned here, if you look at your calculator, you should actually see the same, I guess Desmos wouldn't show you, but if you had a handheld calculator near you, you should be able to see that on your calculator. But you are squaring the whole thing, so just kind of keep that in mind. So, but yeah, you have your new equation of a circle using the cosine and sine functions now. So this also represents your circle. And again, you should be able to recognize that this is also related to the Pythagorean theorem. So this is actually called your Pythagorean identity for any angle theta. So you can see if you go back to what we talked about in section 5.1, we went from Pythagorean to the distance formula to the circle equation, and now we're kind of reversing that. We go from the circle to the Pythagorean formula here, right? So we're just kind of working our way backwards, except this time we're using sine and cosine functions. So this is your Pythagorean identity using the cosine and sine functions. They're telling you one use of this identity is that it helps us to find a cosine value of an angle if you already know what the sine value would be, and of course, vice versa. So one thing to keep in mind is in this case, it will yield two possible values, and we will need to figure out of the two possible values, which one is the one that we are actually looking for, which one is the desired one. So let's take a look at how to go about doing that. So here you can see we are given the sine of theta as 3/7. They're telling us theta is in the second quadrant, and they want us to find cosine of theta, right? So just to give you a quick image, if we're talking about the angle being in quadrant 2, remember that means this point is going to be somewhere over here on our circle. So using this Pythagorean identity, cosine squared plus sine squared equals 1, we will of course go ahead and replace your sine of theta with 3/7. And then since you have to square it, you can see that's where the 9/49 is coming from, right? After you have squared it. Then to get cosine squared by itself, we would go ahead and subtract both sides of this equation by 9/49. So you can see on the right-hand side, you will end up doing 1 minus 9/49. Now you can do this by hand. You can use a calculator to simplify this. It's whatever you are comfortable with. But just to show you very quickly, you would find your common denominator, which would be 49. So you can see when you do 49 minus 9, that's where the 40/49 comes from. So that's how they came up with cosine squared is going to be equal to 40/49. I cannot remember if I had talked to you guys about this or not, but anytime you introduce a square root, right? Because you were given cosine square, we just want cosine by itself. So you have to take a square root on both sides. So let me actually show you something here. So since we are, as a calculation, introducing the square root, you actually have to take into consideration that square root can be a positive root or a negative root. So that's where this plus or minus sign is coming from, is because you can end up with one positive and one negative answer. So go ahead, simplify your radical, and you can see this will simplify into plus or minus 2 times square root of 10/7. Yes. That will happen a lot, Nathaniel. So yeah, we are not technically thin air, but we're definitely pulling out numbers here. So now this is what they were talking about, where they said you will come up with two possible values, and then you need to know which one is the desired value we are looking for. So here's what I want you to think about. Since we know that the angle theta has to be in the second quadrant, remember your cosine value is associated with the x coordinate. So think about this. Of course, sine represents the y values. So we know in the second quadrant, all the y values are going to be positive, and we can see that our sine was a positive value. But we know all the x values in the second quadrant are actually going to be less than 0, which means your cosine value is actually going to be negative. So you can see they're telling you that because you are in the second quadrant, your x value would be negative, which would then in turn make your cosine value be negative. So in this case, you would actually go ahead and discard the positive solution, and you would only keep the negative solution. So that was that additional information which comes from which quadrant is your angle going to be into, and that helps you find will cosine be positive or negative. So I'm going to give you a minute to think and let me see if you have any questions and why cosine came out to be a negative answer. So it's really just because the angle is going to be in quadrant 2 is what tells us that cosine needs to be a negative number. Okay, I'm seeing something. Very good, Zadek. Yes, if you were finding this in quadrant 3, because quadrant 3 also your x values would be negative, so the cosine would be negative. But in that case, remember your sine would also be negative, right? Because the y values are also negative in quadrant 3. But yeah, exactly. That's how you need to think about is based on the quadrant, you would then need to see what your x and y values would be in terms of positive and negative, and that would affect your sine and cosine. So very good. Any other questions, guys? Alrighty. If you do have something, let me know. Okay. Um, so let's take a look at this little description here. All right, so we're saying that you may have noticed at this point, we haven't found any cosine or sine values for angles that are not on an axis. So again, to do this, when the points are not on an axis, we need to work with triangles for that. So they're saying, okay, consider a point on the circle, which is going to be at a 45-degree angle. So right over here. So 45 degrees in radians would be pi over 4. And then we are saying, okay, at this angle, the x and y coordinates of the corresponding point on the circle will be equal because 45 degrees divides the first quadrant in half. So we know going from here, which is remember your initial side, and if this is your terminal side, then we know this is going to be a total of 90-degree angle, right? So if 45 degrees is going to be half of that, we of course know that this length over here is going to be equal to this length over here. So saying based on that, we can tell that your x and y values will be equal because of dividing that quadrant in half. So if your x and y values are the same, the sine and cosine values will also actually be the same. And you can see by using the Pythagorean identity over here, we can verify that. So you've got cosine squared of pi over 4, and again, we're sticking with radians here, plus sine squared of pi over 4 equals 1. Since we know both of these values are going to be the same, you can actually, instead of writing sine squared, we can just replace it and say, since it's equal to cosine, we'll just use cosine squared of pi over 4. So that's, of course, 1 plus 1 will give you 2. So this becomes 2 times cosine squared of pi over 4. Divide both sides by 2. So obviously, You're dividing both sides by 2, so it cancels here. You get 1/2 on the right-hand side. Now, we know we are looking at quadrant 1, which means when you take a square root on both sides, we are only going to keep the positive root, right? We don't have to worry about the negative root because we know both x and y values will be positive and positive. So you will just end up with cosine of pi over 4 is equal to square root of 1/2. Go ahead and rationalize your denominator. And if that is something you want to review, let me know. But rationalizing the denominator basically means get rid of the radical in the denominator. So basically, if I rewrite this guy as square root of 1 over square root of 2, so just kind of breaking up that radical, rationalizing means remove the radical from the denominator, and you can kind of see the math over here of doing that, but you will basically end up with this guy being equal to square root of 2 over 2. And this tells us that at a 45-degree angle, the value of your sine and cosine functions is actually going to be square root of 2 over 2 for both sine and cosine, which in turn means for both x and y. So you will actually see that they are all going to have the same value. Now, I know I showed you the unit circle on the very first day of class, but you can see those are the same values we have here for our x and y coordinates. This is, of course, our 45-degree angle with pi over 4 for radians. But look at all the other quadrants. So 135 is obviously a multiple of 45, right? Now, because this is quadrant 2, of course, you can see there's a negative sign on the x value, but essentially x and y have the same value just with a negative on the x. In quadrant 3, both x and y are negative, so you can see at, again, the multiple of 45 is 225. You will have negative square root of 2 over 2 for both x and y. Quadrant 4, x is positive, y is negative, so you will see, again, same square root of 2 over 2, but one is positive, one is negative, right? So that's basically what happens at those 45-degree angles is you are going to end up with the same values, just the signs will change, right? Okay. They are saying find the coordinates of a point on a circle which will have a radius of 6 at an angle of pi over 4. Now, we know with pi over 4, you should be at square root of 2 over 2, but then how does the radius 6 come into play, right? So let's take a look at that. I guess it's right here. So in this case, the only thing that's going to matter is going back to that formula. Where are you? These here. So you will need to use these formulas here because they do take the radius of the circle into consideration. So we will need to use these. And then you will have your answer. So you can see for x, you are using r times cosine theta. For y, you are using r times sine theta, right? So you've got your radius of 6. You've got your theta. So yeah, 6 times cosine of pi over 4 will become 6 times square root of 2 over 2. Of course, 2 goes into 6 3 times, so that's where you get 3 times square root of 2. And obviously, same thing happens here, and you end up with the same answer. Now, obviously, your x and y values should still be the same because you are still using 45 degrees or pi over 4. So we know the sine and cosine will have the same value. It's only based on the radius that coordinates will change. But otherwise, that ratio, that proportionality still stays the same. So yeah, just to show you what happens when you are looking at a different radius. I guess I should mention that when we are talking about these points here, we are essentially saying you are looking at a unit circle, which means your radius was 1. So I think that's the only difference, is why these guys stayed at square root of 2 over 2. What happens at a 90-degree angle if you have a radius 3? So remember, we already looked at this 90-degree angle previously. So right here, you can see that we got cosine of 0 and sine of 1. So again, that proportionality does not change, right? So we know cosine is 0 at 90 degrees, sine is 1 at 90 degrees. So using that, you can see it doesn't matter what your radius is. You've got your radius of 3. So again, you do 3 times cosine of pi over 2, which is 3 times 0 will give you 0. For a radius of 3, sine is going to still be 1. So 3 times 1 will, of course, give you 3. So your x and y values will go up to 3. So the idea is, if you had a circle with radius 1, or if you have a circle with radius 2, at radius 1, you would be at 0 and 1, right? At radius 3, you would be at 0 and 3. So it's just the radius that will affect the values. Any questions on that? Okay. Um, okay, so what about a 30-degree angle? So what happens when you have to find sine and cosine at a 30-degree angle, or in radians, that would be pi over 6. Of course, we go ahead and draw our circle with the triangle on the inside. Just going to expand this a little bit so you can see that circle a little bit better. And then I can, oops. Make it a little bit smaller later on. But yeah, you can see that we have our circle over here with that 30-degree angle, from your initial side. So let's see how that can help us find, what the values for sine and cosine will be. Okay. So if you have a 30-degree angle, they're basically saying create a reflection of that. So you're basically creating another triangle below the x-axis, which will, of course, because we would be going in a clockwise direction, this angle would be negative 30 degrees. So we're saying, okay, if you combine the two right triangles together, what are you going to end up with? Well, actually, in this case, if you take the total angle measurement over here, obviously positive 30, and you are adding 30 degrees going downwards, right? So you're not going to obviously end up at 0 degrees, right? You're going to be having 30 degrees up, 30 degrees down, which means that will be a total of 60 degrees. Now, if one angle is going to be 60 degrees, then the other two are also going to be 60 degrees, which means what you now have is an equilateral triangle, right? All three sides and all three angles will actually be the same measurement. So all sides will be the value of r, because that's the radius of your circle. So all of these lengths or the sides of your triangle will be the same length, and all three angles will be 30 degrees. So we are saying you can use that idea. So we're saying the vertical line will have a length of 2y. So what do they mean? So they're talking about this length over here. Remember, this is the vertical distance between your point xy and the x-axis. Remember, this distance is going to be y. And if this is the other half of that, this will also be a distance of y. So that's why they are saying you're going to end up with a total vertical length of 2y when you add these guys together. And since all the sides are going to be equal length, that means your radius is also obviously going to be equal to 2y, which you can see that's where you are getting this formula from. So if radius is 2y, you can rewrite that by dividing both sides by 2. and you end up with y equals r over 2. So now using your sine function, right? Sine is y over r. So if y is r divided by 2, r of course is r. Go ahead and simplify that. You can see the r and r will cancel out, leaving you with 1/2. So if the sine function of pi over 6 is 1/2, put it into your Pythagorean identity. You can see that will help you come up with the cosine function value over here. And the cosine function, hold on, sorry. Okay, I'll have to do that later on. So the cosine function, as you can see, once you simplify it, you will end up taking square root over here. Again, since we are on the positive quadrant 1, you will ignore the negative root and just keep the positive root. So you get square root of 3 over square root of 4, which of course square root of 4 comes out to be 2. And you can see your cosine comes out to be square root of 3/2, and sine function comes out to be 1/2, and that's going to give you your x and y coordinates at the 30-degree angle, or basically pi over 6 in radians. And again, we can go back and look at the unit circle. Here's your pi over 6 or your 30-degree angle, and you can see you're going to be at square root of 3 over 2. 1/2, go to the negative 30-degree angle, which is this guy here. Y value will be negative in quadrant 4. Go to the multiples of 30-degree angle over here, and you can again see what these values are going to be. So it's kind of really neat to see how there is some sort of symmetry, right? I mean, obviously, based on the quadrant, you have to do positives and negatives. But if you can get comfortable with that first quadrant from 0 to 90 degrees, it's actually easy to translate it as you go into quadrant 2, quadrant 3, and quadrant 4. So basically, guys, are you seeing how we are coming up with the x and y coordinate values using the Pythagorean identity, knowing what the angle measurement is, and then, of course, kind of doing the math going forward from there. So any questions, any part that is like you are unsure about or you would like any more information on? Are we okay so far? And I know once you start practicing on your own, you will feel more confident as you get to practice it and do a little bit math on your own. But you can just kind of see the breakdown here, how they're showing you, excuse me, working with the triangles here inside your unit circle. So you can kind of see they're talking about this distance here being, that y coordinate or the 1/2 value we got from the sine, and then this distance here will obviously represent the x coordinate or the x value that we got from the cosine function, which was the square root of 3 over 2. But look what happens when they create a reflection of this triangle on the line y equals x. So you can see how when this triangle was reflected, so just imagine if you fold your piece of paper along this dotted line of y equals x, how that triangle will transfer over here. And then in this case, and I don't know if you guys remember inverse functions from your college algebra days, but remember when you create an inverse by reflecting on the line y equals x, your x and y values switch places, right? So what was x over here, remember this was the x value and this is the y value. What was x in the first function actually becomes the y in the reflection or in the inverse function, and then what was y in the first function will become the x in the inverse function. So these are basically coming from inverse functions. Yeah, so Nathaniel, yeah, we will not be worrying about 1.4 for that. For the Friday deadline. Yeah, so don't worry about 1.4. Any questions on this one here, guys? Actually, it looks like we do have a little bit more of 1.3 that we need to talk about. So I may actually give you guys a little bit extra time on the 1.3 homework also. But any other questions at this time? So do we understand how the reflection is working here, guys? I really need you to know why, when you are reflecting on the line y equals x, your x and y values switch places. No? Okay. So remember inverse functions. What inverse functions means? Addition is the inverse function for subtraction. Multiplication is the inverse function for division. A square is an inverse function for a square root. So basically, what one function does, the inverse function will undo. And that's basically what's happening over here is you can kind of see how they are talking about here. So if your angle is at 0, if your angle is at 0, you are going to be right here at the starting point, where we know our x value will be positive 1 and y value will be 0. If you are at a 30-degree angle, so 30 degrees, your x value would be at square root of 3 over 2, y value would be at 1/2. If you are, I know there's a question on chat, just give me 1 minute, guys. 45-degree angle, we know breaks up the quadrant into two equal halves. So your x and y value are going to be same. However, when you talk about the 60-degree angle, that 60-degree angle is what this reflection is talking about. So remember, basically we are saying it's 30 degrees from the vertical line. This angle is 30. But when you go from the horizontal line, that's actually a 60-degree angle. So when you do this reflection based on this line here, it's actually going to create a 60-degree angle. And a 60-degree angle basically creates an inverse value. So sorry, I know I've got like a whole bunch of writing over here, but basically that's telling us your x and y values are switching places. So look at this. Between the 30 and the 60-degree angle, you have actually switched places, but also notice between the 0 and the 90-degree angle, you have also switched places with your x and y values. So they are acting as inverse of each other. They are acting as reflections based on that line y equals x. So that's what's happening over here in these. Yeah, R will stay the same, Zadok. So yeah, it doesn't matter what the radius is because remember we said irrespective of the radius, that proportionality or that ratio stays the same. So yeah, it wouldn't matter what the radius of your circle is. These values are going to switch. So remember that 45-degree angle is also where your line y equals x passes through. So wherever you're seeing that dotted y equals x line here, this is actually going to be right at your 45-degree angle. So this is where your x and y values stay the same. Between the 30 and the 60-degree angle is where the inverse happens. And then, of course, between the 0 and the 90-degree angle is also where the inverse value happens. All right, guys, we will stop right here. We are actually beyond our time. But if you have any questions, I'm happy to stay back and answer any of those. And if not, I will see you on Tuesday. So for now, 1.2 is the only homework that's due tomorrow. And then I'll put new due dates for 1.3 and 1.4. Okay. Have a good evening, guys. Enjoy your weekend. Stay safe, everyone. See you next week. Bye-bye. Bye, guys. Thank you.
Thank you. You as
See ya. Take care.